Okay, let's talk about page 4 of differential calculus. Okay, so the derivative function. In a curve, the slopes of the tangents of the function f of x at various points are different. Sometimes it is possible to define a function, a gradient function, which yields the gradient of the function for any value of x within the domain of f of x. Sometimes the gradient function is read as f dash of x, which is written as f dash of x. When I was a kid, we learned it as f prime of x. F prime of a is a specific gradient of the tangent of f of x at the point where x equals a. Okay, so what does the first sentence say? It just talks about what we discovered in the investigation, okay, that you could take a curve, you could measure the slopes at many points on the curve, you could take those slope values, which are the red numbers in the investigation, and then you could take those red numbers and graph those red numbers in a new graph, and that would become the gradient function or the derivative function. Remember that in IB, gradient is synonymous with slope. Okay, you're never going to see the word slope in the IB exam. You're only going to see the word gradient. When you see the word gradient, remember that's a slope. Okay, so that's what the first sentence is saying. And then this other sentence here is just talking about notation. So we don't want to call the derivative of f of x something completely different, because then we kind of lose track of what it is the derivative of. So what we do is we just put this little prime or this dash here next to the f, and then that means, okay, this is a graph of the slopes of f. It's not the function f of x, it's a related function, f dash of x, okay? And if we put the a value or a certain value inside the function's parentheses instead of instead of x, then what we're doing is we're saying, okay, we are going to use a specific value like 5 or something like that, and then it'll give us a numerical value back, right? Because a derivative function is just another function. It doesn't have a specific value. But once you narrow it down and say, okay, give me the slope at a certain point on the curve, then the derivative function is going to give you an exact value back. So, okay. All right, so let's look at some examples of that. So number 1, using the graph below, find f of 2 and find f dash of 2. Okay, so they're not expecting us to take derivatives here. They're just expecting us to look at the pictures and then conclude what is the height of the function at x equals 2 and what is the slope of the function at x equals 2. First of all, let's find x equals 2. X equals 2. It doesn't exactly say where 2 is, but it's a horizontal line. So it doesn't vary the height or the slope. So that's why they're not giving us the x scale. So you can see that, like, if this is 2, then I could say, okay, what is the height of the function at x equals 2? Of course, it is height 3 because this is a horizontal line. It's always height 3. And then we want to know what is the slope at x equals 2. And since it's a horizontal line, the slope is always 0. So we know that f dash of 2 is 0. So you see, like, f of 2 and f dash of 2 look very similar in notation, but they're equal to completely different things because f of 2 is just asking for the height of the function, the y value, and f dash of 2 is asking for the slope of the function, the slope of the tangent line of the function. Okay. Number 2, using the graph below, find f of 0 and f dash of 0. Okay, so in this case, it is not a horizontal line, it's a diagonal line. Since they give us the y value in the x, or the y-intercept and the x-intercept of the function, we could figure out the slope of the function just by using, middle school methods. The rise is -4, the run is +4. -4 divided by +4 is -4/4, which is -1. So our slope of this line at any point is -1, right? So the slope is -1. They're asking us for the height of the function at x equals 0, so it would be right here, the height is equal to 4. They're asking us also for the slope of this function at x equals 0. So that would be the slope here. Remember, the slope at any point on this diagonal line is -1, so the answer here would be -1. Okay. Number 3, consider the graph alongside. Find f of 2 and f dash of 2. Okay, so here they put x equals 2 here. Here they need to be very specific because this is a curve, so the slope is constantly changing. They gave us information about this line, indirect information, which is sufficient to figure out both the slope and the height here. Let's see. So it goes through, this line goes through the point 0, 1 and 4, 5. What is the slope of this line? Let's see. If we drew a triangle here, it would be 4 across, and it would be 4 up because 5 minus 1 is 4, 4 minus 0 is 4. So it is a 45, 45, 90 triangle. It's a triangle that's perfectly diagonal. It has a slope of 1, right? So the slope of this is 1. And what is the height of at x equals 2? So since we know that this tangent line that they drew for us is tangent to the curve at x equals 2, we know that the height of this line at x equals 2 is the y value we're looking for. So let's see. The height at 0 is 1. The height at 1 would be 2. The height at 2 would be 3 because it's a slope of 1, right? That makes sense, right? And then if we go over to x equals 3, it would be height 4. If we go over to x equals 4, it would be height 5, so it works out. So the height is 3 here. So the height is 3, f of 2 is 3, and f dash of 2 is equal to 1. Okay? Okay. All right, now let's go down to the last definition, which is important to, even if we don't use completely this definition, and you're not responsible for knowing this definition, but this part of the definition is something that you should know, even if you don't understand how to use this definition to calculate the power rule, which is, what is the derivative of x to the 4th? It is 4x cubed. Okay, that's the power rule, right? We can use this formula to calculate the power rule, but you don't need to know how to do that. But we do need to understand what are the parts of this because it helps us understand what is a derivative. Okay, remember how I always say the derivative is the slope? Well, the part of it that looks like a slope is this part here. So let's see what I mean by that. Let's say that I have a function, a curve, and it goes through these 2 points. Okay, one of the points is x equals 5, y equals f of 5. The other point is x equals 6, y equals f of 6. Now, notice I did not put y values here. I just said, I plug 5 into the function and I get a value, which is going to be the y value. It's a number. I don't know what it is, but I wrote it here. And when I plug 6 into the function, I get f of 6. That's also a number. And I just drew a diagram with the 2 points there. Okay. Now, if I was to find the gradient between those 2 points, I could use the slope formula. So I could take f of 6 minus f of 5 for the y value, for the rise, and then I could do 6 minus 5 for the run. Okay, so do you notice that I have found the slope of between these 2 points by subtracting the y values and subtracting the x values? That's all there is. Okay. By the way, what is the distance between the first x value and the second x value? 6 minus 5 is 1. Okay, so the difference between 5 and 6 is 1. Why am I talking about that? I'm going to show you in a second. Okay, So this definition here is just like a general way of saying this exact same thing. So instead of 5 and 6, I'm going to use x equals x. That's a little confusing that x equals x first. And then for the second value, I'm going to use x plus h. Okay? So basically you can imagine, okay, the first x is 5. The second value, which is 6, is x plus h. So basically it's like saying 5 plus 1. Okay, so my two x values that I'm going to use are 5 and 6, and here I'm writing them as 5 and 5 plus 1. So in this case, what's h? It's 1, right? Because the distance between 5 and 6 is 1. Okay, instead of putting 5 and 6 and h, I just put x plus h, and h. Why am I doing that? Because what I'm going to do when I do calculus is I'm going to take these 2 points, which are far apart, and I'm going to gradually slide them together until they're right next to each other. And when I do that, instead of having a line connecting these 2 points, what I'm going to have is a tangent line which is hugging the curve at x equals 5. Okay, and so the reason why I make this a variable instead of h equals 1 is because I want to make it adjustable, and I'm going to make h go to 0. Okay, so eventually this triangle becomes very, very small, and it becomes the value of the derivative, because the derivative is the slope at a single point. It's not the slope between 2 points. So the way they figure that out is they put 2 points that are far apart, and then they slide them together until they touch each other by taking the limit. Okay? So what you do need to know is you do need to understand this process of finding a slope, which you do understand when it's numbers. When it has these variables, notice that I'm sure you understand now how we got x and x plus h. Now how do we get the y values? We just plug them into f, just like we did here. So instead of f of 6, we have f of x plus h. And instead of f of 5, we have f of x, and those are my y values. So you can see that, like, if I take the second y value and I subtract the first y value, I get the numerator here. If I take the second x value and I subtract the first x value, I get the denominator, which is just h. Okay, so that's where this comes from. That's why it's a slope. Derivative is a slope. This is exactly why the right half of this expression looks like this. Okay? All right. You may not totally understand that now, but eventually, after working with this, then during the next couple of days, I think you'll be there. Okay. Write 3 different ways of representing the derivative function. Okay, we're just learning more notation. So like the first one that we just learned is f dash of x. It could be also y dash, right? Because the function f of x could be just y. We often call the derivative of y dash. And then finally, there is dy dx. Okay, dy dx is similar to another notation that we have learned in the past, delta x divided by delta y divided by delta x. Remember, this is the equation for slope. Now, they've replaced the deltas with d's because what we do is we take the slope formula, but then we're going to take the delta x and we're going to take the limit as it goes to 0. And then this becomes dy dx. So dy dx is related to delta y over delta x, but there's a limit there. And we just use d's instead of the delta. Okay, and this notation has a lot of useful properties that we're going to take advantage of in the next chapter of calculus that we do.